Last video, we saw what a continuous function is and saw what it means for a function to be continuous at a point C. Today we will see that we can combine continuous functions to form new continuous functions. More precisely, if the constituent functions are continuous at a point C, then the combination is also continuous at the point C. One of the definitions of continuity was in terms of limits, and we have already seen limit theorems, and this will be our first approach towards combining continuous functions. So let f and g be functions from a set A to the set of real numbers, where A is some subset of R. Now if C is a cluster point of A, then we know that limit x tends to C of f plus g of x is equal to limit x tends to C of f of x plus limit x tends to C of g of x. Now if f and g are continuous, then we can say that this will be equal to f of C and this will be equal to g of C. When is this true? This is true precisely when f is continuous, and this is true if g is continuous. Thus, if f comma g are continuous at C, then limit x tends to C f plus g of x is equal to f of C plus g of C, which is equal to f plus g of C, which will imply that f plus g is continuous at C. So if C was a cluster point and f and g were continuous at C, then f plus g is also continuous. On the other hand, if C was not a cluster point, then by default f plus g is continuous at C. Hence, if f and g are continuous at C, then f plus g is also continuous at C. And notice, moreover, that there is nothing special about plus operation here. The exact same argument could have been used to show that f minus g will be continuous if f and g are continuous at C. Similarly, f into g is continuous if f and g are continuous at C. And I leave these two as a homework. Let me reiterate the homework problems. So let's say homework. The homework is that show that if f and g are continuous at C, then f minus g and f into g are continuous at C. But we had one more theorem for limits, one for quotients. But there were some subtleties in that result, right? Like the thing is, if we want to define f of x by g of x, then g of x cannot be 0 because we don't know how to divide by 0. So because of that, we do not want g of x to be equal to 0. So if g of x, if in addition to the earlier condition, if g of x is not equal to 0, then limit x tends to C f of x by g of x is equal to limit x tends to C f of x divided by limit x tends to C of g of x. But this is equal to, if f is continuous, then the numerator is equal to f of c, and if g is continuous, then the denominator is equal to g by c. But this is equal to f by g of c. Hence, so let me just Write this down. If f and g are continuous, then this happens. So what do we have as a result? If f and g are continuous at C and g of x is not equal to 0 for every x in A, then f by g is continuous at C. So that is the last result we have about algebraic operations on continuous functions. You have already seen why this is useful when you learn limits, but you will see that we get a really rich class of continuous functions as soon as we have these theorems. So let us see what is this rich class of continuous functions we have at our disposal. So we saw that if two functions are continuous, their sum is also continuous. And we have seen this kind of argument before. If sum of two continuous functions are continuous, then sum of n continuous functions should also be continuous. And we generally prove this using induction. And the exact same thing can be done here as well. And I leave that as an exercise. So the homework for you is that if f1, f2, etc. up to fn are continuous at C, then first of all f1 plus f2 plus etc. up to fn is continuous at C. Secondly, f1 into f2 into etc. fn is continuous at C. How do you prove this? You prove this using mathematical induction. So I want you to do this as an exercise. But what do we gain from that? Let us get to that next. We know that f of x is equal to x is continuous at all points. This implies that g of x equal to x power n is continuous at all points. Okay? Why? We are using the second result from the homework. f1 into f2 into etc. up to fn is continuous. What are the fi's? All the fi's are equal to f of x. Right? So g of x is equal to f power n of x. Now this implies that the function, let's call it g dash of x, is equal to an x power n is continuous, where an is a constant. Okay? And this will tell you finally that h of x is equal to a naught plus a1x plus a2x squared plus etc. up to an x power n is continuous. What are we using here? Here we are using the first problem from the homework. How are we using it? f1 is equal to a naught, f2 is equal to a1x, f3 is equal to a2x squared, etc. So let's write it down. This is equal to f1, this is equal to f2, this is equal to f3, this is equal to fn. And we are using homework 1 to prove this result. And this tells us that every polynomial is continuous. Now we are going to use the result we just proved, namely that polynomials are continuous, to get an even bigger class of continuous functions. To do this, let p of x and q of x be polynomials. Moreover, q of x is not equal to 0 for all x. Then p of x by q of x is continuous. Okay. Why? Because if f is continuous and g is continuous, then f by g is continuous. But why did I write this separately? Because this is an important class of functions and these are called rational functions. So rational functions are of things of the form p of x by q of x, where the numerator and denominator are polynomials. To give an example, what we want to see is something like, let's say, let r1 of x be equal to x square plus 3x plus 2 divided by x minus 1. Is it continuous at x equal to 3? And I don't know what you will guess, but you cannot really use any of the results we have shown till now. Why? Because the q of x that we have, that means the denominator we have, is not non-zero at all points. Because if we want to use the theorem that we just proved, we want q of x to be non-zero for every x in the domain. And we do not have that. Why? Because for x equal to 1, the denominator is 0. So we cannot use the theorems that we have seen so far to show that the function x squared plus 3x plus 2 divided by x minus 1 is continuous at 3. On the other hand, intuitively we feel that this function should be continuous at x equal to 3. Why? Because, see, in some sense, what are we doing when we are checking the continuity of a function at a point? We are looking at the function's behavior near the point 3. Correct? See, we had converted the metaphor of motion or approaching the point to proximity. That means near the point. So the continuity of a function at 3 should only depend on the behavior of the function near 3. And 3 is not super close to 1. It's not like very, very far, but it's far enough for when you take limits and stuff like that. And that's precisely what we want to make precise soon. Okay, that means what we want to say is that there exists an epsilon neighborhood around 3 which does not contain 1 for some epsilon. And that's precisely what we mean by two elements being far from each other. So we can find some epsilon neighborhood of 3 such that one does not fall inside that epsilon neighborhood. And if we can do that, then we are really interested in only the behavior of the function in that epsilon neighborhood. So this is the intuition we will now make precise. To do this rigorously, we first have to understand what we mean by restriction of a function to a subset of the domain of the original function. So let us say that f is a function from a to r, where a is a subset of the set of real numbers. And let b be a subset of a. Okay, if you say that g is a restriction of f to b, what we mean by that is g is a function. This is what we mean is g is a function from b to r such that g of x is equal to f of x for all x in b. And here, notice that I have used a notation. I wrote something like this, which means that f is restricted to b. I will often use this notation. And now we are in a position to formally state the theorem we were hinting at. F from a to r is continuous at C if and only if there exists a delta naught such that f restricted to A intersection C minus delta naught to C plus delta naught is continuous at C. The proof of theorem is not difficult at all, but the reason why I stated is because it's very powerful. So the statement is important. The proof is actually quite simple. Anyway, let us go through it. Proof. Okay. F from A to R is continuous at C. By what we mean by that is, for every epsilon greater than 0, there exists a delta that depends on epsilon, which is also greater than 0, such that mod of x minus c is less than delta implies that mod of f of x minus f of c is less than epsilon. One thing to notice that is that here this x actually belongs to A. Let us also give a name for this function that we get after restricting f. Let's call this function g. Okay. So now if you take a point x in A intersection C minus delta naught to C plus delta naught. Okay. Then this x will belong to A. And therefore, if mod of x minus c is less than delta, notice that here this x is actually in A intersection C minus delta naught to C plus delta naught. Okay. If we have this, then mod of g of x minus g of c, here notice that g of x is equal to f of x and g of c is equal to f of c. Hence, mod of g of x minus g of c should also be less than, it is equal to mod of f of x minus mod of c, f of c, and hence that is less than epsilon. And this implies that g, which is f restricted to A intersection C minus delta naught to C plus delta naught, has to be continuous. Now we might be tempted to do the exact same proof to do the other direction, but there is a catch. Notice that here the statement is for elements in A. And the advantage was that this set, which is A intersection C minus delta naught to C plus delta naught, is a subset of A, and hence whatever is true for elements of A will be true for elements of the subset. But when we try to prove the other way, we cannot do this because A is a bigger set than A intersection C minus delta naught to C plus delta naught. So we have to do a little trick, and that's what I will show next. So what we are given is G from A intersection C minus delta naught to C plus delta naught to R is continuous at C. This is equivalent to, for every epsilon greater than 0, there exists a delta that depends on epsilon, which is also greater than 0, such that mod of x minus c is less than delta implies that mod of g of x minus g of c is less than epsilon. Notice here that this x belongs to A intersection C minus delta naught to C plus delta naught. As described earlier, x belongs to A does not imply that x belongs to A intersection C minus delta naught to C plus delta naught. So we cannot directly use the kind of argument that we used before. But on the other hand, notice that if x belongs to A and mod of x minus c is less than delta naught, then we can say that this implies. We can say, so if this is the case, we can say that x belongs to A implies that x belongs to A intersection c minus delta naught to c plus delta naught. So what will you do now? See, now we want to find a delta of epsilon that works for f, right? So let's call this new delta delta dash, okay? So how do you define delta dash of epsilon? I define delta dash of epsilon to be minimum of delta of epsilon and delta naught. Let us see what can we conclude if mod of x minus c is less than delta dash of epsilon. Here, notice some things. Notice first of all that x belongs to A here. Okay. So now this thing implies that mod of x minus c is less than delta naught, because delta dash of epsilon is less than delta naught, less than or equal to delta naught, hence mod of x minus c is less than delta naught. Moreover, x belongs to A. So together x belongs to A and x mod of x minus c is less than delta naught. Together this implies that x belongs to A intersection c minus delta naught to c plus delta naught. Moreover, this implies that mod of x minus c is less than delta of epsilon. Why? Because delta dash of epsilon is less than or equal to delta of epsilon. So we get that as well. So together what do we have? X belongs to A intersection c minus delta naught to c plus delta naught, and mod of x minus c is less than delta of epsilon. So if both of these are satisfied, what do we have? We have that this implies that mod of g of x minus g of c, mod of g of x minus g of c is less than epsilon. But what is g of x minus g of c? That is equal to mod of f of x minus f of c. So mod of f of x minus f of c is also less than epsilon, which will imply that f is continuous at c. Hence, we have proved that if g is continuous at c, then f is also continuous at c, thus completing the proof of our theorem. Now that we have this theorem, let us revisit to our function r1 of x is equal to x square plus 3x plus 2 divided by x minus 1. Now this function is not defined everywhere. So either we have to say what is the domain of this function, or we have to give a function, tell what happens when x is equal to 1. So let's just do that. Let's say that this is equal to 0 if x equal to 1. I'm just giving some random number. If x equal to 1, I'm just giving it 0. And all other values, if x is not equal to 1, then I define this. So this function is defined at all points at least. Now the question is this continuous or not? Is r1 of x continuous or not? We cannot use any of our theorems to prove this. However, notice that let's call p of x is equal to x square plus 3x plus 2, and q of x is equal to x minus 1. Notice that p restricted to 2, 4 and q restricted to 2, 4 are continuous at 3. Moreover, what we have is q restricted to 2, 4 of x is not equal to 0 for all x, which implies that p restricted to 2, 4 closed interval, let's open interval 2, 4 divided by q restricted to 2, 4 is continuous at 3. Okay. Now r1 of x restricted to 2, 4 is equal to p restricted to 2, 4 divided by q restricted to 2, 4, which implies that r1 of x restricted to 2, 4 is continuous. Correct? finally notice that this 2 comma 4 is nothing, the open interval 2 comma 4 is nothing but a delta neighborhood of the point 3. The delta naught neighborhood according to previous theorem. And what is the delta naught? The delta naught is equal to 1. So this 2 comma 4 is equal to 3 minus 1 to 3 plus 1. So by the previous theorem, even the bigger function r1 of x is continuous at 3. And this is the kind of argument I want you to be comfortable with. Another important way of combining two functions is composition of functions. Let us see what happens to the composition of two functions. So let f be a function from a to r and g be a function from b to r. So we want to look at g composed with f of x, which is defined as g of f of x. So you take an element x, act f upon it, and the result you act g. But as you can clearly see, this cannot be always defined. The functions f and g needs to satisfy some conditions so that this can be defined. More precisely, what we want is we want f of x to belong to b. Only then we can act g upon it, because the domain of g is b. So f of x should belong to b, and this should happen for every x. So what does that mean? This means that the image of a under f is contained inside b. If the image of f is contained inside b, then we can take g composed f of x. Let us write that precisely. If f of a is contained inside b, then g composed with f is a function from a to r. Okay, so in that case we can define g composed with f from a to r. Under these conditions we have, if f is continuous at c and g is continuous at f of c, then g composed with f is continuous at c. How do we prove this? The proof is again quite simple. G of f is continuous at c if and only if for every sequence xn such that xn converges to c, f of xn converges to f of c. For this purpose, let xn be a sequence such that xn converges to c. This means that f of xn converges to f of c. Why? Because f is continuous. Now f of xn is a sequence that converges to f of c, and g is continuous at f of c, which implies that g of f of xn converges to g of f of c. Why? Because g is continuous. So we have that g of f of xn converges to g of f of c, and as xn was an arbitrary sequence that converges to c, we see that g of f is continuous at c. Hence the theorem is proved. Let us see a quick application of the theorem we just saw. So we know that x can be rewritten as x minus y plus y. Okay. Now if I take mod on both sides, using triangle inequality, I can write this as this is less than or equal to mod of x minus y plus mod y. Correct? Which can be rewritten as mod x minus mod y is less than or equal to mod x minus y. But using the exact same argument, you could have shown that mod y minus mod x is also less than or equal to mod of x minus y. But what does this mean? This means that mod x minus mod y is greater than or equal to minus of mod x minus y. So what does this mean? This statement plus this statement, 1 plus 2, means that mod of mod x minus mod y is less than or equal to mod x minus y. This means that the function g of x is equal to mod x is continuous. Why? Take delta of epsilon is equal to epsilon. Thus the previous theorem tells that if f from a to r is a continuous function, is continuous at c, let's say, is continuous at c, then mod f from a to r is continuous at c. Why is this the case? The function mod f is nothing but g composed with f, and g is continuous everywhere, f is continuous at c, so mod f is continuous at c by the previous theorem. Now if you play around with a lot of functions, you will get a better feel of the power of these theorems. So please do that. Okay, that's all for this video. In the next video, we will talk about properties of a continuous function on an interval. See you next time.